Thank you, Daniel, and hello, everybody. My name is Fernando Cantú. I'm the Chief Statistician of UNIDO, the UN Organization for Industrial Development. And today I would like to give you just a brief summary of our experience with nowcasting and some of the challenges we have faced. In particular, one of them, which is the issue of model selection. So I will start sharing my screen. Dan, can you please let me know if you see it?
Yes, it's working.
Okay, thank you. Okay, so Dan already provided some background on nowcasting, so I will, which is very good. And I just as an additional piece of the context, I want to mention that there has been a growing interest in all these sort of predictive analytics in the context of development, particularly since the start of the SDGs. As you know, there's many indicators associated with the SDGs, more than 200. And when people started to look at them, they saw that in many cases, the data was just not there, or it was there, but it was old or incomplete. And this really presents an obstacle because we have a set of targets that we want to accomplish by 2030, but we have not a lot of supporting evidence of where we were at baseline and where we're heading to, and if we are moving in the right direction or not. So there has been a lot of initiatives and I think this has been very good for statistics, particularly in the context of development. A lot of efforts to bridge these gaps by improving data production at the country level, but also by using different sorts of analytics to fill the gaps as much as possible, when possible. So here I have some quotes from this Global Partnership for Sustainable Development, which are the main partners, I guess, or one of the main partners for Data for Now initiative. But this is also mentioned, for example, in the Secretary General's data strategy that was released, I see 2021 is a mistake, it should be 2020, last year. And also in the system-wide roadmap for innovating UN data and statistics that very explicitly mentions the issue of nowcasting. So it's great, there's a lot of interest on this. For us, it opens up a lot of very interesting areas of work, but it's also brings a lot of challenges. And this because SDG indicators, they are all over the place. There's many different areas, very different levels of aggregation, and some of them we can get a lot of information of what's going on, some of them less. So let's say, it brings up a lot of challenges on how to do any sort of predictive analytics on these indicators. Also, another problem is the custodian agencies for the SDG indicators are not expected to only provide kind of a global estimate or a regional estimate, but more and more people are requesting country level data, and even more disaggregation in, I don't know, going by industry if it's an economic set, or by population group if it's a kind of a social development indicator. And the custodian agencies have to respond to all these and to provide the required information to a wide audience made of statisticians, but also policymakers and other users with, of course, very limited resources. So there is a need for nowcasting methodologies that are transparent, easy to communicate, easy to explain and to describe, that perform well, obviously, but also that are simple and can be scalable to this kind of multiple estimates that are required in this SDG era. So we are UNIDO, we are custodians for 6 SDG indicators, all of them in SDG 9 related to industry. So we're not one of the most we're one of the traditional ones. Is just manufacturing. That's one of the variables that are most followed in economics. So there's a lot of history of forecasting or monitoring these variables. And you would say, well, maybe there's not a need for nowcasting in this context because there's a lot on data in industrial production. Many countries have industrial production indices that can be used. But the problem is that, as Dan was mentioning before, that not all countries have these indices of industrial production. Some of them have monthly, some of them have quarterly only. Some of them are released very late. And also, and very importantly, the SDG 9 indicators are based on manufacturing value added, which is a concept from national accounts, and doesn't necessarily match always the concept of manufacturing output or production. So of course, they're very related, but they're not the same. So at UNIDO, we took this challenge and we decided to implement a dynamic factor model using an EM implementation. As you can see, this is the one used by the Fed in New York, by the European Central Bank, or was used. So it's a very common methodology. And for now, this is a work in progress. We're starting with the kind of regional and global nowcast. So we're trying to estimate global manufacturing value added and by main regions in the world. But later on, we want and we have to expand to country level nowcast and even in some cases industry level at the ISI 2-digit level at least. See here, I will present a couple of results using just as an illustration the global manufacturing value added. So the first thing when we started this exercise, we started to think, okay, what variables we can put into the nowcast can give us information about what's happening on global manufacturing value added. And we came up with obviously a huge list of hundreds and hundreds of indicators. So the question was, what variables should we keep in the model? And I feel that this has been a relatively neglected area in the nowcasting literature. Many of the papers on nowcasting GDP or other macro aggregates, they just start with a list of indicators and then they apply the methodologies. And I guess this makes sense in those situations because there's a lot of work being done in this area. So I will not say there's a consensus, but at least there's a lot of experience and a lot of work on which variables proxy or coincide with the trends in GDP and can be good candidates for nowcasting. But in other contexts, it's not as obvious. Industry or manufacturing value added is also fairly straightforward, but I'm also want to expand to kind of a general situation where you're asked to nowcast a random sustainable development indicator, and you have a lot of candidate variables, and you have to decide which ones should be included and which one not. And also, of course, when we're dealing with regional or global variables, then the available indicators multiply because we also have the country level information there that we can use separately. And that could also provide information. And as has been mentioned before, this creates a curse of dimensionality where we becomes more and more demanding to estimate these. Sometimes impossible because we have many more variables than observations. And of course, there's a huge risk of overfitting. Plus, it's very taxing to maintain and then to communicate the results from the point of view of an international organization. Okay, so this is not a trivial problem as well. So here, what I did is back in maybe May, I was doing testing the model for and see how it was indicating for the first quarter of 2021. And this is a quarterly growth rate. And I created 100 models taking 10 variables at random from a pool of about 300, 320 potential candidates. So I took 10 variables at random, and then I saw what was the nowcast for the first quarter of 2021. And you see here the results. You see it's all over the place. Most of them are concentrated between 1% and 2%. Some of them go up to 3%, which is a huge rate for not huge, but it's a big rate for a quarterly growth rate. Some of them are even negative. So it really makes a difference which model you take. It will produce different results. Maybe you are thinking, oh, but 10 variables is a very simple model. If you put more, maybe it will improve the performance, and it does. Here, the blue histogram is 20 models with 20 random variables. So it's more, it converges more to around 1.5, but still there's a wide variance in the estimators. Also, with hundreds of variables, it's impossible to test all of them. And even if you use standard kind of selection, model selection procedures, it's also not possible. It's just not possible to do. Backward elimination, you have to start with the entire model, and that cannot be estimated in many cases. Forward selection will force you to test thousands and thousands of models. That is also not feasible in general circumstances. And contrary to, or in general, there's no theoretical model to guide you. So we at UNIDO, we settled, at least for now, in a kind of ad hoc alternative. We adapted these two papers on model selection, Kai Alia, Heitz Alia. And here the idea is to just not take all the candidate variables or candidate indicators in the same way, but impose some sort of structure in an exogenous way, like from based on subject matter knowledge or previous experience or what other estimates say. And this, the idea is that of all the potential candidates, we can divide them into groups that make sense from a kind of subject matter point of view. And this group structure will really help us into move forward with the model selection. I will go into a bit more detail on the algorithm later, but first I want to talk about the selection criteria. So here we don't really use metrics based on significance, because as we know, there's so many variables that we can just add more variables and increase the significance with a huge risk, obviously, of overfitting. But this cannot really be used. Also, the kind of change of estimate metrics are of limited interest here, because we're not really interested in the coefficients of the dynamic factor model. Sorry. We can use them, of course, to test the stability of the model, but this is not the main objective of the estimate. So we also do a kind of a out of sample validation, very simple, where very classical. We divide the sample into two, a training and a validation set. We estimate the parameters of the model in a training set, and then we evaluate the performance on the validation test by using a very simple metric, the absolute prediction error. So what is the algorithm? So we start by, so imagine we have hundreds of variables, potential variables. We start with an initial model with a very limited number of key variables. For example, in the what Julia presented at the beginning, she said that there are some known drivers of food insecurity, like conflict, drought, etc. So we can use some of them as a kind of an initial set, but this is optional. We can also start with empty sets. So we divide all the variables into G groups, and then we do separate forward selection for each group using just prediction error as a selection criteria. Like that, we will have some models by group. Then we put all the variables together into some sort of supergroup, supermodel that has all the variables. But of course, these variables have never interacted with one another. So then we estimate the model and we do a backward elimination to see which ones we can start removing. And the variables that are dropped go back to their original group. And then we iterate this process until convergence. Until, let's say, at the forward selection step, no more variables get added. And then at the backward elimination step, no more variables get dropped. So the model becomes stable. I mean, I will not talk too much about the selected groups, but based on experience and the kind of variables that we have, we created these seven groups, yes, of variables that, for example, for us, we know that we cannot really put together the industrialized economies with the developing or emerging economies because they follow really different trends. So that's why we create two groups separating the indicators there. We also have something on supply and demand, some on the PMIs, for example, etc. And this is a performance. Normally, in our experience, this converges very quickly. So here is the initial kind of this, just the key variables that we took. We took about 6 or 7, so just a very skeletal model to get started with. That was not a very good fit. But then by the first iteration, the average error goes down to a very low number, and then it kind of very quickly converges, so that between the fourth and the fifth iteration, there was no change in the variables included in the model, and we stop. So it was the convergence criterion, and this is our final model. And for us, it has worked really well. It's relatively fast. It's also an automatic algorithm, which is important when in the future, when we have to do this kind of country level nowcast. So it's something that we can program, or we have programmed, and we can just implement at the country level and to arrive to the final model. So just as a conclusion, I think these kind of ad hoc solutions are criticized there because there's not really we cannot really evaluate if they're optimal, if they really reach the best model or not. But I think it makes it gives a good balance of something that it's performing well. So here we're testing a lot of models. We're still testing all the variables repeatedly. So we're sure that none of them just get neglected or forgotten there. And also it remains feasible. It's something that can be done relatively quickly in any normal computer. So I think it strikes a good balance. Of course, this bringing kind of this non-statistical information from the subject matter knowledge, it may not be well seen, but this is something very common, like in many of the other exercise on nowcasting, this list of exogenous indicators is also introduced at the beginning. So I think it's kind of part of something that needs to be done. And what it does is what makes the model, it gives a structure to the model and makes the estimation feasible. Of course, as Dan was mentioned before, there's a lot of developments in this kind of high dimensional data spaces modeling in machine learning and in other shrinkage model that we also will have to, or will want to explore. There's also this discussion of which one is better, sparse modeling versus dense modeling. Sparse modeling is something like I describe here, where only a few of the indicators are taken as relevant, and the other ones, their coefficients are basically restricted to be equal to 0, versus a dense modeling where this is determined within by using the information provided by the data itself. I mean, this is something that we still need to explore and see if it's feasible in such a situation, but it's also worth exploring. So it's a very quick walkthrough of what we're doing. We will publish a working paper, hopefully in the fall. So there will be more information there, and there's my email as well in case you have any questions or you want to discuss this further. I will, as Dan, I will also, once this is ready, I will make the code available for anyone interested in reproducing this. So thank you so much. Thanks,
Fernando. So I don't see any questions in the chat if another participant wants to ask one. If not, I had one or two questions. So one question was about the possibility of these sort of meta model predictions. So in the machine learning context, it's perfectly normal and common to take the output of many different models and a sort of meta prediction. And when I see the graph of your random sampling of variables, and you get this almost like a normal distribution centered around something, do you think that there's any maybe one day scope for research or interest in saying, what if we took that mean, that 1.5 of your distribution as the prediction, even if no individual model said that, and you wouldn't necessarily have coefficients producing that output, but obviously there's some sort of information content there where these models are centered around a certain number, and that potentially could be useful to take as a prediction. Do you think there's any scope for that in this field that you're talking about, or that's a bit too lacking in hard, interpretability?
No, I think this model averaging it's a common process. It's used. I would say that there's studies and there's evidence of its performance. and how it works in different situations. The problem here is it will still require to estimate many models, which can become problematic in this situation. So it's not that we don't want to explore. I mean, we're obviously happy to explore, but we really want to confine ourselves to things that we can easily implement and reproduce. Also remembering that we cannot just, invest 1 month of all of our computers and run all the models and that's it. But this model needs to be recalibrated frequently. So it's a kind of an ongoing process that we also need to take into account. So of course, there's a lot of options to explore, but we're really trying to keep this kind of computational time low.
Makes a lot of sense. I had one last question, if no one else had one. Algorithm sounds very interesting and very relevant for any model selection, but especially nowcasting where you have so many potential explanatory variables. I was just curious how the runtime of the algorithm scales with the number of variables. So say you had 10 potential variables and you double it to 20. Will this algorithm actually take the same amount of time, or will it take twice? Will it take squared? Like, how does it scale to the number of potential variables?
Yeah, I don't have that information right now. It's something that, as you say, it's something very important to track and keep an eye on it, and we will definitely do in the paper. But it is exponential. Like you show in your graph, if you double the number of variables, it will not take double time. It take more because there's all these variance and covariance that needs to be estimated as well. So yeah, it increases substantially. So
sense. Cool. So there's nothing else. It's again right on time to move ahead to Rosa's presentation. So Rosa, you have the floor.